Hello everyone, in this video we're going to be talking about some of the common ways of converting alkenes to alcohols. So three techniques or three methods that we're going to be using here would be the acid-catalyzed hydration, then we got this oxymercuration-demercuration, and this hydroboration-oxidation. And it's extremely important to know the difference between those three. I'm going to be talking about the mechanism on the acid-catalyzed hydration, and that's going to be the most common one. I'm now going to be talking about the mechanism on the oxymercuration, demercuration, and the hydroboration oxidation in this particular video. I'll have a separate video if you need to know the mechanism for that. But for the most part, you don't really have to know the mechanism for the later two methods. So what's going to be the generic reaction? So obviously the generic reaction is going to be I have an alkene, so CH2 double bond is CH2, and I'm adding water in there. And obviously you're not going to be adding water in case of hydroboration oxidation. It's going to be a little bit different way of doing it, but at the end product is going to be still similar, still going to be making an alcohol, but just in the overall conversion of an alkene to an alcohol, you start out with an alkene and you add a water in under acidic conditions, let's say, and then we're going to be making an alcohol. So if I go ahead and change the color of this water molecule to, let's say, this orange, then what's going to happen, I still have this CH2, single bond CH2, but now one of these hydrogens is going to be coming from the water, and it's going to be connected to one of the carbons, and the other carbon is going to be getting the alcohol. So that's how you're going to be making an alcohol in this particular case. And if I want to go ahead and write that down in the form of skeleton structure, this would look like this simple alcohol here. Now that's your generic reaction, but obviously you gotta be really careful with the Regis selectivity and the stereochemistry of these reactions. So I'm going to talk about first the acid-catalyzed hydration. And in the acid-catalyzed hydration, the Regis selectivity is going to be the Markovnikov addition, where the electrophile or the hydrogen gets connected to the carbon that already has more hydrogen atoms attached. So I'm not really going to draw the hydrogens here because it's important to kind of get in the habit of knowing where the hydrogen is going to go without drawing all the hydrogens on the skeleton structure. So I got this carbon number 1 and carbon 2. And if I want to name the number the other ones, that would have been 3 and this is 4. And since we're doing this acid catalyzed, so I'm going to have water and acid. So let's say I got an hydronium ion in there. So your first step is going to be the nucleophile, which is going to be your double bond, attacking this, grabbing this proton here, and this is going to break up to lose water here. Now, this hydrogen is being grabbed by the pi bond, which is made between the carbon 1 and 2. So the question is, where would your hydrogen actually go? Would that go on the first carbon, or would that go onto the second carbon? And the answer is, it's going to go onto the first carbon. So I'm not really going to draw that, but assume that went onto the first carbon, and now first carbon has 3 bonds, but then as a result, this second carbon becomes electron deficient, and that makes a secondary carbocation. And you don't want to be making the other way, where you don't want to be having this hydrogen going on to the second carbon. In that case, your first carbon would be the carbocation, and that would be your primary carbocation. That's going to be less stable. So you're always going to be making a more stable carbocations. Now, what happens in the next step? So in the next step, we're going to have this nucleophile coming in. So your nucleophile obviously is going to be the water. So remember, you lost the water in the first case. So I can go and write that down there. And your water is the one that's going to be doing the nucleophilic attack here, and that's going to be doing the nucleophilic attack on this particular carbocation. So I could have an attack on to the top side, or it could do a attack on to the bottom side. So either one of those ways are going to be fine. So you have almost a 50-50 shot of doing that. And in the process, what happens, you're going to be having this water molecule attacked either coming out of the page or going back into the page. So if I want to focus on maybe only on one of them, but make sure you draw the second product at the end of the day. So I can have this water molecule attached, but now coming out of the page like this to get a positive charge on here. So then I got to do the acid-base reaction back because this is an acid-catalyzed reaction. So you got to make sure you retrieve your acid back at the end of the day. So this is how it's going to look like. So it grabs that proton and it restores the electron density back onto that oxygen. So your product would have the alcohol made here, and it's going to be coming out of the page. And remember, if I had done that back the bottom attack, which would have the water coming behind the page, then you would have this OH at the end of the day going back into the page, like this one right here. So you have a possibility of making both of those um, stereoisomers there, or another way of saying you have a possibilities of making these enantiomers there. So that's going to be your stereochemistry for this particular reaction. So make sure you know the regioselectivity. So the regioselectivity, it's going to be doing the Markovnikov addition, and your stereochemistry is going to be you can make both enantiomers, and you have to worry about that if it is indeed a chiral center. If it's not a chiral center, then you don't have to worry about the stereochemistry that much. Okay, since you're making the carbocation, there are always going to be the possibilities of carbocation rearrangements, and that's one of the drawbacks of these acid-catalyzed hydration. So let's look at this particular example here. So suppose I'm running an acid-catalyzed hydration on this particular alkene here. So if I quickly run in a mechanism there, so this is going to be attacking this proton here, and that's going to be coming out. So one of your products, I mean your intermediates rather. So I'm just gonna be copying this just for the sake of time. So where your carbocation is going to be, well, remember your carbocation is going to be right here because your hydrogen is going to go on to the first carbon and your second carbon becomes electron deficient, making a secondary carbocation. Now, anytime you're making a carbocation, be on the lookout for making it a more stable carbocation. So in this case, I could do a 1,2 hydride shift there. So remember, if I can move this hydrogen onto this location there, in that case, I would be moving the positive charge onto this new location, and that's going to be your tertiary carbocation. So I would say it's going to be a 1,2 hydride shift. So then you got this tertiary carbocation made. And then at the end of the day, I'm going to have the water attacking now. So the water that you have created and the first step, it's going to be attacking right there. Make a curved arrow there. And in this case, whether you do a top attack or bottom attack, it doesn't really matter because this carbon that's grabbing this nucleophile, which is the oxygen in water, is not chiral. So since it's not chiral, you don't really have to worry about the stereochemistry. So you still want to go ahead and do the acid-base reaction at the end of the day so that you have your alcohol. So after running the carbocation rearrangement, you are going to be making this particular alcohol here. And that's going to be one of the drawbacks of doing these acid-catalyzed hydrations. Now, suppose how would I really make this instead? So remember what happens when we did an acid-catalyzed hydration. We made this guy right there where the OH was on the tertiary carbon there. But what if I really want to make this guy right there? How would I do that in that case? I can't really run acid-catalyzed hydration because it's going to do a carbocation rearrangement. So as a result, we got to figure out another way of doing it, and that's going to be your oxymercuration-demercuration. So that's going to be the difference in the end products. It's still going to be the Markovnikov addition. However, there's no carbocation rearrangement. And in terms of stereochemistry, it's going to be an anti-addition. So I'll talk about that in a minute, but I'll focus on what is going to be the benefit and what's going to be the reagents that you're going to be using. So you're going to be using a and the first step is going to be the mercury acetate, so HgOAc2, and you're going to be using a nucleophile, so this is going to be water. So I want to make a note on here. You don't necessarily have to have only water as your nucleophile. Obviously, if you're making alcohols, then you can use water, but if you're making some sort of ethers, then you may very well be using like alcohols like CH3OH, or even like amines could be used sometimes as well, depending on what you're really trying to make at the end of the day. So that's your first step, and your second step is going to be carried out by this reducing agent, which is sodium borohydride, so NaBH4. So that's going to be the reagent for performing this task, making sure it's going Markovnikov addition. However, there is not going to be any carbocation rearrangements. So this is going to be an anti-addition. So remember, your hydrogen goes onto the first carbon, and your oxygen or the OH goes onto the second carbon, just like you would see in a typical Markovnikov addition. So when we say an anti-addition, what that really means, those OH and the hydrogen would be added anti to one another. Now, sometimes it may not matter, but sometimes it would matter. So how would that look like? Well, I could have this, suppose this OH is coming out of the page momentarily. So if that's coming out of the page, then your hydrogen on that first carbon would be going back into the page. And clearly, you don't really have to worry about that hydrogen because that carbon number 1 is not a chiral center. So you don't really have to draw that. So um, in addition to that, you could also have this OH going back into the page. So you could very well have a second product. In the second product, so I'm going to write down plus there, I would have this OH going back into the page. And in that scenario, this H would be coming out of the page because they need to be anti to one another. Now, they make a set of enantiomers, obviously, in this particular case. And like I said, you don't really have to worry about drawing the hydrogen. So I did draw those here just to kind of show that they're anti to one another. But I want to go ahead and take those out because because your carbon number 1 is not really a chiral center, so drawing those hydrogens out of the page or back into the page doesn't really make any difference. So this is what your product's going to be. Let's look at another question where, okay, what if I want to make this particular um, product here, with this particular alcohol? So what's really the difference between this alcohol that we're trying to make and the one we just made earlier? Well, if you look at it, it's actually an anti-Markovnikov addition where your OH is getting added to that terminal carbon that has more hydrogens attached to it. So that particular reaction would be called an hydroboration oxidation. And as the regioselectivity is going to be, it goes anti-Markovnikov addition. And in terms of stereochemistry, it's going to be a syn addition. So extremely important to know what a syn addition and an anti-addition is. So in the case of syn addition, both of those incoming atoms or group of atoms, like in this case hydrogen and the OH, they're going to be either both coming out of the page or they both going to be going back into the page. And obviously you have to worry about it if you have a chiral center. Now, what's going to be the typical reagents for this? In the first step, you're going to be using BH3 THF. So THF is your solvent, BH3 is obviously your Lewis acid there. And in the second step, you're going to be using H2O2 and NaOH. So when I go ahead and do this anti-Markovnikov addition, and like I said, it's going to be a syn addition, that means I could either have both of those coming out of the page, so this OH would be coming out of the page, and the hydrogen that's getting added onto the second position would also be coming out of the page like this. But in this particular case, you don't really have to worry about drawing those out of the page or a possibility of going back into the page for both of them because they're not chiral centers. So you have to worry about it if they were indeed the chiral centers. But remember, this is going to be a syn addition. Okay, so those are going to be the most important reactions in case of making the alcohols from alkenes. And remember, oxymercuration-demercuration still does Markovnikovs, but no carbocation rearrangements. And if you want to somehow attach, if you want to make an alcohol that's an anti-markovnikovs, you're going to be using hydroboration-oxidation. I'm not going to be showing the mechanisms for those because a lot of times you don't have to know the mechanisms for those particular reactions if you're taking in a sophomore organic chemistry. But obviously, there are going to be some professors that would require you to know the mechanisms of those reactions. So I'll have a separate video where I'll talk about the mechanisms of this oxymercuration, demercuration, and hydroboration oxidation. But it's very common and it's important to know the mechanism of this simple acid-catalyzed hydration. All right, let's look at a couple of examples here and see what's going to be the differences in those hydroboration oxidation and oxymercuration demercuration products. So I'm going to just go and copy this down here and bring that down here. Let's try to overlap it on it. Okay, I'll take that arrow out. So we are doing the oxymercuration demercuration for this first step. I do want to change this water or into a set of different nucleophiles so you guys can see the difference, what other products you can make. So instead of using water, I'll use CH3OH. And clearly you want to kind of look at your double bonded carbons, and I'm going to have one here and two here. And your one is going to be the most substituted carbon, then the two. So this D is the heavier isotope of hydrogen. It's called deuterium. So it's still going to be considered as similar to hydrogen in terms of that being less substituted. So when I'm looking at the Markovnikov's addition, your OH or your um, methanol here in this particular case should go onto the first carbon and your hydrogen should go on to the second carbon. And remember, it's going to be an anti-addition. So if I go ahead and just copy this down. So I'll go ahead and take out this bonds for right now. So at the end of the day, your products would be, in one case, I could have this still going to be Markovnikov's addition, so the OCH3 here. So instead of having an alcohol, because you're using the methanol, and that's going to be pushing this methyl group back into the page like this. And then what's going to be happening to your D here? Well, remember, this needs to be anti to one another. So your hydrogen onto the second group needs to be going back into the page. So your anti means if your this methoxy group, or if that was an alcohol group, was coming out of the page, then the added hydrogen onto the second carbon will be going back into the page. So that's what makes them anti to one another. And then obviously, what's that going to do to the D? That's going to be pushing the D out of the page. So you want to draw the D out of the page. And it's important to draw both of those here in this particular case because you have multiple chiral centers. You got this is a chiral center, that's a chiral center, and obviously you have another chiral center that we didn't even touch. So that's another thing you want to kind of worry about. So that's going to be your one product. Your second product, what if it's the other way around in terms of stereochemistry? So if I just take these out for momentarily. So you could have your this methoxy group going back into the page, and what's that going to do to your methyl? That's going to be pushing that methyl coming out of the page like this. And then in that case, your incoming hydrogen is going to be coming out of the page because it needs to be anti to that methoxy group, and that's going to be pushing your deuterium back into the page. So that's going to be your two products in that case. And what's going to be the relation between those two products? Well, they're not an enantiomers because remember there was a third chiral center that we didn't really touch. So they're not mirror images of one another. So that means they are going to be the diastereomers. So you're not going to be always be making an anti-merge. Sometimes you make diastereomers if you have another chiral center that you're not touching at all. Let's look at this next one. So in this next one, we are doing hydroboration oxidation. So let me just copy down this reagents here. Okay, so this is actually going to be anti-markovnikovs. So your OH is going to be on the second carbon, obviously, and it's also going to be the syn addition. So if I want to just go ahead and copy this down momentarily, and maybe change the color there. Let's get that to be yellow. So since it's an anti-Markovnikov's addition, your OH needs to be on the second carbon. And let me take out this double bond here. If I go ahead and put my OH coming out of the page, suppose, then your deuterium will be pushed back into the page. And then the H that's going to be added onto the first carbon needs to be syn with respect to the OH. So that means that H should also be coming out of the page. And that would push this methyl group back into the page. So that's going to be one of your products. And obviously your second product is what if they were flipped in terms of stereochemistry. They were both going back into the page. So what I want to do here, erase all that. So now I could have this OH going back into the page. If that OH is going back into the page, the hydrogen on carbon number 1 should also be going back into the page because they needs to be sent to one another, and that methyl will be pushed out of the page, and so is this deuterium group will be pushed out of the page like this. So those are going to be your two products there, and what's going to be the relation between those two? Well, they're still going to be diastereomers because remember, they're not mirror images because of this third chiral center that didn't really get flipped. So this is how your product's going to be looking like in terms of regioselectivity, which means Markovnikovs or anti-Markovnikovs, and in terms of stereochemistry, which means it could be an anti or it could be a syn addition. All right, if you have any questions on any of those, feel free to leave any comments in the section below.